how we get a brilliant idea out of our heads and into a computer? I mean, how do we get a machine to actually understand what we want it to do? It's one of the biggest questions of our time, really. So let's dive right in and unpack how computers, well, how they think.
Just think for a second about the app you use every single day. Maybe it's for getting around town, catching up with friends, or just killing time with a game. It feels seamless, almost like magic, right? But behind that slick screen is a very, very carefully written recipe. So what's the secret sauce?
Well, the secret is something called a computer program. And honestly, it's not as complicated as it sounds. It's really just a list of instructions that we write out telling the computer exactly what to do step by step. It's the bridge that connects what we want to do with what the machine actually does.
Okay, so how do we actually build that bridge? That's what we're going to get into first. We're going to follow the journey from a spark of an idea all the way to a set of rock-solid instructions that a computer can follow without getting confused. You know, the really cool thing about programming is that it's not just one thing. It's this amazing mix of being an art. You need creativity and a sense of design to make something that people actually enjoy using. And it's a science because it relies on pure logic and methods that have been proven to work. And to practice this art and science, programmers need tools, right? Well, their most important tools are programming languages. You can think of them just like any other language, except instead of talking to other people, you're using them to talk to a computer. And this visual here, it just perfectly shows that whole journey. See, at the very top, you've got a program written in a way that's pretty easy for us humans to read. Then that gets translated down into something a little closer to the machine's own language. And finally, all the way at the bottom, you get the raw ones and zeros that the computer processor actually understands. This layering effect is a super powerful idea called abstraction. Think about it like driving a car. You don't need to know how the engine combusts fuel. You just need to know how to use the steering wheel and pedals. Abstraction lets us do the same with computers. So let's break down those levels a bit more. A high-level language is like giving a friend simple directions. Hey, walk to the end of the block and turn left. Easy, right? A low-level language is more like describing the physics of every single muscle you need to fire to take each step. One is simple for us, and the other gives you insane control over the machine itself. And it doesn't stop there. Languages also differ in how the computer reads them. Some are compiled, which means the entire program gets translated into machine code all at once, before you even run it. It's kind of like translating a whole book before you read it, which makes the actual reading super fast. Others are interpreted, and they're translated line by line as the program is running. A little slower maybe, but way more flexible. Now, let's think about the difference between what you actually see on your screen and all the magic happening behind the curtain. The front end is everything you see and touch, the buttons, the layout, all of that. Think of it as the dashboard in your car. The back end is the engine under the hood. It's the server, the database, all the heavy lifting you don't see. But here's the thing. Before a programmer touches any of these languages, before they write a single line of code, they need a plan. You wouldn't build a house without a blueprint, right? Well, it's the same thing here. And in computer science, we call that blueprint an algorithm. So what in the world is an algorithm? Well, the formal definition can sound a little intimidating, but all it really is a recipe. It's the step-by-step logic that tells you how to get from a problem to a solution. That's it. And the funny part is, you use algorithms all the time without even thinking about it. Just turning on your computer is an algorithm. You have to check the cables, then turn on the power strip, then the computer, then the monitor. If you do it out of order or skip a step, it doesn't work. See? That's an algorithm in action.
But of course, not just any old list of steps makes for a good algorithm. A good recipe has to be crystal clear, no confusing instructions. It has to actually end at some point. You can't have a recipe that just tells you to stir forever. And every single step has to be something you can actually do. These simple rules are what make algorithms so incredibly reliable. Right, so if an algorithm is like a recipe, it makes perfect sense that you wouldn't use the same recipe for every dish. Programmers have tons of different types of algorithms, each one designed to solve a specific kind of problem. Let's take a quick look at a few. First up, we've got a strategy called divide and conquer. The name says it all, really. You take a huge, scary problem and you break it down into smaller, bite-sized pieces. You solve the little pieces and then you put them all back together. It's like looking for a name in a phone book. You don't start at page 1, you jump to the middle, see if you need to go forward or backward, and you keep cutting the problem in half. It's incredibly efficient. Then you've got the total opposite, the brute force approach. This one isn't fancy, but it's simple. You just try every single possible answer until one works. Think about a keychain with 100 keys. You just try them one by one until the lock opens. It's not elegant, but hey, it gets the job done. Next, there are greedy algorithms. These guys are the optimists. At every single step, they make the choice that looks like the absolute best option right now, hoping it leads to the best overall solution. Your GPS does this. To find the fastest route, it's constantly picking the next road that seems to get you closer to your destination at that very moment. And finally, let's talk about backtracking. This is a clever one. It's all about trial and error. You try going down one path, and if you hit a dead end, you backtrack. You go back to your last choice and try a different option. This is exactly how a computer program can solve a really tricky Sudoku puzzle. Okay, so we've looked at the languages and we've looked at the blueprints. Now let's tie this all together and bring it back to your world. Because these ideas, as abstract as they might seem, are the invisible engine running pretty much everything you do online. So why does any of this matter? Because a really well-designed algorithm is basically a superpower. It lets us solve problems incredibly fast, saving time, money, and energy. It makes sure that everything from your bank balance to your map directions is accurate, and it allows these systems to work for billions of people all at once. That's why big tech companies are in a constant race to invent better, faster algorithms. So here's a little challenge for you. The next time you get a movie recommendation, or see a certain post at the top of your feed, or follow your GPS through a city, just take a second and remember, you are having a direct conversation with an algorithm. This stuff isn't just theory, it's the invisible architecture of your daily life. So there you have it. From a simple idea to a language to a recipe, we've seen how these logical blueprints make our modern world go round. So I'll leave you with this thought. Now that you know the basic ingredients, what problem would you teach a computer to solve?